Memory System 1.
Learning objectives. At the end of this topic, you will be able to define memory system of the computer, state the need for memory system, explain memory hierarchy of the system, describe the function of ROM and RAM chips, demonstrate the connection between CPU and memory system.
Outcomes. By the end of this topic, you will be able to apply the basic concepts, semiconductor RAM memories and ROM memories in computer design. Identify the memory technologies in computer and be aware of the way in which the technology is changing.
Memory refers to the physical devices used to store program or data on a temporary or permanent basis for use in computer. It is a collection of storage cells together with associated circuits needed to transfer information in and out of storage. What is the need for memory unit? According to von Neumann, all the programs and related data are supposed to be stored before it is executed. And if the computer system is to execute instructions one by one, receiving it from the user, the speed of work would be slow. So a fast memory device can be used to store a huge set of instructions together before it can execute. A memory hierarchy in computer storage distinguishes each level in the hierarchy by response time. Since response time, complexity, and capacity are related, the levels may also be distinguished by the controlling technology. The three key features, which are a constraint to the design of a computer memory, are capacity, access time, and cost. The memory must be capable of storing huge amount of data. To achieve greatest performance, the memory must be able to keep up with the processor. The cost of memory must be reasonable in relationship to other components. There is a trade-off among the three key characteristics of memory, namely capacity, access time, and cost. A variety of technologies are used to implement memory systems, and across this spectrum of technologies, the following relationships hold. Faster access time, greater cost per bit, greater capacity, smaller cost per bit, greater capacity, slower access time. As one goes down the hierarchy, the following occur: decreasing cost per bit, increasing capacity, increasing access time, decreasing frequency of access of the memory by the processor. Main memory. The main memory is the central storage unit in a computer system. It is large and fast memory used to store program and data during the computer operation. The principle used for the main memory is based on semiconductor integrated circuits. RAM is the working memory in a computer. It is a computer storage location that allows information to be stored and accessed quickly from random locations. RAM chips are of two types: static, dynamic. Static RAM, SRAM. The static RAM consists essentially of internal flip-flops that store the binary information. The stored information remains valid as long as power is applied to the unit. It is easier to use and has shorter read and write cycles. SRAM is used in implementing the cache memory. Dynamic RAM. DRAM. The dynamic RAM stores the binary information in the form of electric charges that are applied to capacitors. It offers reduced power consumption. It has larger storage capacity. DRAM is used in implementing the main memory. Read-only memory, ROM. ROM is a type of built-in memory that is capable of holding data. It is used for storing the bulk of the program and data that are permanently residing in the computer. The ROM portion of main memory is needed for storing an initial program called a bootstrap loader. The Bootstrap Loader is a program whose function is to start the computer's software operating when the power is turned on. Since RAM is volatile, its contents are destroyed when power is turned off. The contents of ROM remain unchanged after power is turned off and on again. RAM and ROM chips. A RAM chip is convenient to communicate with a CPU. A bidirectional data bus that allows the transfer of data either from memory to CPU during read operation or from CPU to memory during write operation. A bidirectional bus is constructed with 3-state buffers. The output of 3-state buffers can be placed in one of the 3 possible states. 1. Signal equivalent to logic 1. 2. Signal equivalent to logic 0. 3. High impedance state. Let us consider the example of RAM chip. The memory size of the chip is 128 into 8 bits per word. This requires a 7-bit address and an 8-bit bidirectional data bus. The read and write inputs specify the memory operation, and the 2 chips select CS control units are for enabling the chip only when it is selected by the microprocessor. The read and write inputs are sometimes combined into one line labeled RW. When the chip is selected, the 2 binary states in this line specify the 2 operations of read or write. The example: operation of the RAM chip. The unit is in operation only when CS1 is equal to 1 and CS2 bar is equal to 0. The bar on top of the second select variable indicates that this input is enabled when it is equal to 0. If the chip select inputs are not enabled, or if they're enabled but the read or write inputs are not enabled, the memory is inhibited and its data bus is in a high impedance state. When CS1 is equal to 1 and CS2 bar is equal to 0, the memory can be placed in a write or read mode. When the WR input is enabled, the memory stores a byte from the data bus into a location specified by the address input lines. When the RD input is enabled, the content of the selected byte is placed into the data bus. The RD and WR signals control the memory operation as well as the bus buffers associated with the bidirectional data bus. The size of ROM chip consists of 512 by 8, 512 into 8. The data bus can only be in an output mode since ROM can only read. The 9 address lines in the ROM chips control the memory operation as well as the bus buffers associated with the bidirectional data bus. The size of ROM chip consists of 512 by 8, 512 into 8. The data bus can only be in an output mode since ROM can only read. The 9 address lines in the ROM chip specify any one of the 512 bytes stored in it. The 2 chip select inputs must be CS1 equal to 1 and CS2 bar equal to 0 for the unit to operate. There is no need for a read or write control because the unit can only read. In this diagram, RAM and ROM are connected to a CPU through data and address bus. The low order lines in the address bus select the byte within the chips, and other lines select a particular chip through its chip select inputs. The selection between RAM and ROM is achieved through bus line 10. The RAMs are selected when the bit in this line is 0 and the ROM when the bit is 1. Address bus lines 1 to 9 are applied to the input address of ROM without going through the decoder. This assigns addresses 0 to 511 to RAM and 512 to 1023 to ROM. The data bus of the ROM has only an output capability. whereas the data bus connected to the RAMs can transfer information in both directions. Summary. Let's summarize the topic.
Memory refers to the physical devices used to store program or data on a temporary or permanent basis for the use in computer. Memory systems serve as a backup for storing the information that is not currently used by the CPU. The three key features which are a constraint to the design of a computer memory are capacity, access time, and cost. RAM is a computer storage location that allows information to be stored and accessed quickly from random locations. The dynamic RAM stores the binary information in the form of electric charges that are applied to capacitors. ROM is used for storing the bulk of the programs and data that are permanently residing in the computer. Memory System 2.
Learning objectives. At the end of this topic, you will be able to list the characteristics of the auxiliary memory devices, explain the working of magnetic disks, understand the working of magnetic tapes, know the method of accessing associative memory, describe the functioning of associative memory.
Outcomes. By the end of this topic, you will be able to evaluate the need for storage standards for complex data storage mechanisms such as DVT. Understand the necessity of memory hierarchy to reduce the effective memory latency.
Devices that provide backup storage are called auxiliary memory. It holds programs and data for future use, and because it is non-volatile, it is used to store inactive programs and to archive data. They are used for storing system programs, large data files. The important characteristics of any storage device are its access mode, access time, transfer rate, capacity, and cost. Access time. The average time required to reach a storage location in memory and obtain its contents is called access time. The access time consists of a seek time required to position the read-write head to a location and a transfer time required to transfer data to or from the device. Transfer data. Transfer rate. The transfer rate is the number of characters or words that the device can transfer per second. Both magnetic drums and disks consist of high-speed rotating surfaces coated with a magnetic recording medium. Bits are recorded as magnetic spots on the surface as it passes a stationary mechanism called a write head. Stored bits are detected by a change in magnetic field produced by a recorded spot on the surface as it passes through a read head. Magnetic disk. Magnetic disk is a circular plate constructed of metal or plastic coated with magnetized material. All disks rotate together at high speed and are not stopped or started for access purposes. Bits are stored in the magnetized surface in spots along concentric circles called tracks. The tracks are commonly divided into sections called sectors. A track in a given sector near the circumference is longer than a track near the center of the disk. Disks that are permanently attached to the unit assembly and cannot be removed by the occasional user are called hard disks. A disk drive with removable disk is called a floppy disk. A magnetic tape transport consists of the electrical, mechanical, and electronic components to provide the parts and control mechanism for a magnetic tape unit. The tape itself is a strip of plastic coated with a magnetic recording medium. Bits are recorded as magnetic spots on the tape along several tracks. Read or write heads are mounted, one in each track, so that data can be recorded and read as a sequence of characters. Magnetic tape units can be stopped, started to move forward or in reverse, or can be rebound. The tape starts moving while in a gap and attains its constant speed. by the time it reaches the next record. Each record on tape has an identification bit pattern at the beginning and end. A tape unit is addressed by specifying the record number and the number of characters in the record. Records may be of fixed or variable length. A memory unit accessed by content is called an associative memory or content addressable memory, CAM. It considerably reduces the time required to find an object stored in a memory. The instruction available in memories like cache, ROM, and virtual memory are addressed by content and not by address location. Hardware organization. Associative memory consists of a memory array and logic for M words with N bits per word. Each word in memory is compared in parallel with the content of the argument register. The words that match the bits of the argument register set a corresponding bit in the match register. Reading is accomplished by a sequential access to the memory for those words whose corresponding bits in the match register have been set. The key register provides a mask for choosing a particular field or key in the argument word. Only those bits in the argument that have ones in their corresponding position of the key register are compared. Suppose the argument register A and the key register K have the below bit configuration. Only the three leftmost bits are compared with the memory words of K, because K has ones in these positions. Let us consider A is equal to 1, 0, 1, 1, 1, 1, 1, 0, 0. K is equal to 1, 1, 1, 0, 0, 0, 0, 0, 0. Word 1 is equal to 1, 0, 0, 1, 1, 1, 1, 0, 0, no match. Word 2 is equal to 1, 0, 1, 0, 0, 0, 0, 0, 1, match. The relation between the memory array and external registers in an associative memory. Associative memory of M words, N cells per word. The cells in the array are marked by letter C with two subscripts. The first subscript gives the word number and the second specifies the bit position. A bit A in the argument register is compared with all the bits in column J of the array. If a match occurs between all the unmasked bits of the argument and the bits in word I, the corresponding bit MI in the match register is set to 1. If one or more unmasked bits of the argument and the word do not match, MI is cleared to 0. Associative memory consists of a flip-flop storage element and the circuits for reading, writing, and matching the cell. The input bit is transferred into the storage cell during a write operation. The bit stored is read out during a read operation. The match logic compares the content with the corresponding unmasked bit of the argument and provides an output for the decision logic that sets the bit in match register. Match logic. The match logic for each word can be derived from the comparison algorithm for two binary numbers. Arguments A is compared with the bit stored in the cells of the words. Two bits are equal if they are both 1 or both 0. The equality of two bits can be expressed logically by the Boolean function. Each cell requires two AND gates and one OR gate. The inverters for A1 and K1 are needed, once for each column. and are used for all bits in the column. The output of all OR gates in the cells of the same word go to the input of a common AND gate to generate the match signal for MI. MI will be logic 1 if a match occurs and 0 if no match occurs. Read operation. If more than one word in memory matches the unmasked argument field, all the matched words will have 1s in corresponding bit position. All matched words are read in sequence by applying a read signal to each word line whose corresponding MI bit is a 1. In applications where no two identical items occur, only one word may match the unmasked argument field. In such case, M output is directly connected to the read line for the corresponding word. The content of the matched word is presented at the output lines and no special read command signal is needed. Write operation. An associative memory must have a write capability for storing the information to be searched. If the entire memory is loaded with new information by addressing each location in sequence. If unwanted words have to be deleted and new words inserted one at a time. For replacing a word tag register, which has many bits as there are words in the memory is used. For an active word, the corresponding bit in tag register is set to 1, and word is deleted from memory by clearing its tag bit to 0.
Summary. Let's summarize the topic. Auxiliary memory holds programs and data for future use, and because it is non-volatile, it is used to store inactive programs and to archive data. Bits are stored in the magnetized surface in spots along concentric circles called tracks. A memory unit addressed by the content is called an associative memory or content addressable memory, CAM. It considerably reduces the time required to find an object stored in a memory. The match logic compares the content with the corresponding unmasked bit of the argument and provides an output for the decision logic that sets the bit in the match register. Memory System 3.
Learning objectives. At the end of this topic, you will be able to define cache memory and explain its importance. Explain the cache memory structure and its working. Know the concept of virtual memory that involves defining address space and memory space. Explain page replacement algorithms. Explain the memory management hardware.
Outcomes. By the end of this topic, you will be able to apply the concept of cache coherency in multiprocessor organization, utilize the various methods of organizing cache memory and analyze the cost-performance trade-offs for each arrangement, analyze the need for virtual memory to the operating system.
According to von Neumann, the CPU fetches each and every instruction with the related data from memory and executes it. The instruction from the CPU to main memory is very fast, and the same instruction from main memory to CPU is slow. To overcome the slow transfer, we introduce a cache memory, which is placed between the CPU and main memory. Cache memory is intended to give memory speed approaching that of the fastest memories available, and at the same time provide a large memory size at the price of less expensive types of semiconductor memories. Size of the main memory consists of 32K by 12, and size of the cache memory consists of 32K into 12, 512 into 12, whereas the cache is a small and fast memory. How does the cache memory work? When the CPU needs to access memory, the cache is examined. If the word is found in the cache, it is read from the fast memory. If the word addressed by the CPU is not found in the cache, the main memory is accessed to read the word. A block of words containing the one just accessed is then transferred from main memory to cache memory. The block size may vary from one word, the one just accessed, to about 16 words adjacent to the one just accessed. In this manner, some data are transferred to cache so that future references to memory find the required words in the fast cache memory. How do we measure the performance of cache memory? The performance of cache memory is frequently measured in terms of a quantity called hit ratio. When the CPU refers to memory and finds the word in cache, it is said to produce a hit. If the word is not found in cache, it is in main memory and it counts as a miss. The ratio of the number of hits divided by the total CPU references to memory, hits plus misses, is the hit ratio. The hit ratio is best measured experimentally by running representative programs in the computer and measuring the number of hits and misses during a given interval of time. Mapping of data from main memory to cache. Three types of mapping procedures are of practical interest when considering the organization of cache memory. 1. Associative mapping. 2. Direct mapping. 3. Set associative mapping. Associative mapping. The fastest and most flexible cache organization uses an associative memory. The associative memory stores both the address and content, data of the memory word. A CPU address of 15 bits is placed in the argument register and the associative memory is searched for a matching address. If the address is found, the corresponding 12-bit data is read and sent to the CPU. If no match occurs, the main memory is accessed for the word. The address data pair is then transferred to the associative cache memory. If the cache is full, an address data pair must be displaced to make room for a pair that is needed and is presently not in the cache. Direct mapping. The CPU address of 15 bits is divided into two fields. The 9 least significant bits constitute the index field and the remaining 6 bits form the tag field. The future shows that main memory needs an address that includes both the tag and the index bits. The number of bits in the index field is equal to the number of address bits required to access the cache memory. In general, there are 2 k-words in cache memory and 2 n-words in the main memory. The n-bit memory address is divided into 2 fields, k bits for the index field and n-k bits for the tag field. The direct mapping cache organization uses the n-bit address to access the main memory and the k-bit index to access the cache. Let us consider the example organization of direct mapping. The index field is divided into 2 parts, the block field and the word field. In a 512-word cache, let us consider the memory address is divided into 2 fields, k bits for the index field and n-k bits for the tag field. The direct mapping cache organization uses the n-bit address to access the main memory and the k-bit index to access the cache. Let us consider the example organization of direct mapping. The index field is divided into 2 parts, the block field and the word field. In a 512-word cache, there are 64 blocks of 8 words each, since 64 into 8 is equal to 512. The block number is specified with a 6-bit field, and the word within the block is specified with a 3-bit field. The tag field stored within the cache is common to all 8 words of the same block. Every time a miss occurs, an entire block of 8 words must be transferred from the main memory to cache memory. Set associative mapping. It is an improvement over the direct mapping organization in that Each word of cache can store 2 or more words of memory under the same index address. Each data word is stored together with its tag, and the number of tagged data items in one word of cache is said to form a set. The fundamental idea of cache organization is that by keeping the most frequently accessed instructions and data in the fast cache memory, the average memory access time will approach the access time of cache. Although the cache is only a small fraction of the size of the main memory, a large fraction of memory requests will be found in the fast cache memory because of the locality of reference property of programs. Cache addresses. When virtual addresses are used, the system designer may choose to place the cache between the processor and the Memory Management Unit (MMU), or between the MMU and main memory. A logical cache, also known as virtual cache, stores data using virtual addresses. The processor accesses the cache directly without going through the MMU. A physical cache stores data using main memory physical addresses. Virtual memory is a concept used in some large computer systems that permit the user to construct programs as though a large memory space were available, equal to the totality of auxiliary memory. Each address that is referenced by the CPU goes through an address mapping from the so-called virtual address to a physical address in main memory. A virtual memory system provides a mechanism for translating program-generated addresses into correct main memory locations. The translation or mapping is handled automatically by the hardware by means of a mapping table. Address space and memory space. An address used by a programmer will be called a virtual address, and the set of such addresses the address space. An address in main memory is called a location or physical address. The set of such locations is called the memory space. Mapping using memory table. The mapping table may be stored in a separate memory or in the main memory. Mapping using paging or page table. The physical memory is broken down into groups of equal size called blocks. The term page refers to groups of address space of the same size as block. The basic components of a memory management unit are: 1. A facility for dynamic storage relocation that maps logical memory references into physical memory addresses. 2. A provision for sharing common programs stored in memory by different users. 3. Protection of information against unauthorized access between users and preventing users from changing operating system functions. Summary. Let's summarize the topic.
Cache memory is intended to give memory speed approaching that of the fastest memories available, and at the same time provide a large memory size at the price of less expensive types of semiconductor memories. The performance of cache memory is frequently measured in terms of a quantity called hit ratio. The fastest and most flexible cache organization uses an associative memory. The direct mapping cache organization uses the n-bit address to access the main memory and the k-bit index to access the cache. Set associative mapping is an improvement over the direct mapping organization in that each word of cache can store 2 or more words of memory under the same index address. Virtual memory is a concept used in some large computer systems that permit the user to construct programs as though a large memory space were available, equal to the totality of auxiliary memory.